Well, I am Massimo Visco of Italian National Institute of Astrophysics, and today I am going to present the result of two experiments, LARASE and SaToR-G. This experiment, these are the people involved in the experiment and the institution. Well, these two experiments are funded by the Italian National Institute of Nuclear Physics, and they are devoted to make a measure of general relativity using geodetic satellite tracking by laser. And a main point of this activity, as yesterday David Lucchesi showed, is modeling of both gravitational and non-gravitational perturbation. Today I will present a measure of an improved measurement of a lens steering effect and a preliminary measurement to constrain Yukawa-like interactions. As I said, we compare the measured orbits of a geodetic satellite with a prediction of general relativity, and you use for our measure LARASE 2 and LARASE. The first part of the presentation is about lens steering precession measurement. This effect was firstly measured using geodetic satellite by Ciuffolini and Pavlis in 2004, and this effect is a precession on the orbit of the satellite due to the angular momentum of the Earth. Here you can find the expression of, and this precession produces a circular effect on two orbital elements, the right extension of the ascending node and the argument of the pericenter. Here are the expressions that are function of fundamental constant, mean Keplerian element, and this parameter is 1 in general relativity and 0 for Newtonian physics. The effect is very small. We expect something like 30 milliseconds of arc here. So we have to fight perturbation, as I said, that produces systematic errors over the measurement, both gravitational and gravitational perturbation. In the main source of error for the measure of line steering is given by the model of Earth gravitational field. And that's why the signature, we have the not spherical symmetry distribution in the Earth produce a precession over the line of node that has the same signature with respect to line steering. And this precession depends over J2 and J4 and the other moment of the gravitational field of the Earth. And the amplitude of the effect due to the modeling of this of the harmonic is higher than the effect we want to measure. So using static model was not possible to reach the level of accuracy that we wanted. And to reduce the impact, we had to use the temporal solution provided by Grace. Here there is an example for a coefficient detent in the range of our measure. If we adopt a static field at this level, we are far from the real measured value. And also, if we adopt an average value, we have some errors. We prefer to adopt a linear interpolation of the temporal solution. To make our measurement, we make a precise orbit determination, and we compute the residual in the orbit elements. The technique, we use an arc length of 7 days, no empirical acceleration, and general relativity is modeled rather than for length steering effect. So we expect to find in a residual the signature of this effect. The analysis method is one that was introduced by Ciuffolini Group several years ago, and is based in measuring not only the effect, the precession of the orbit of a single satellite like the LARASE, but use more than one satellite. In this case, we use the precession of the node of 3 satellites. Each precession depends on a general relativity effect, in this case the line steering, that is parameterized by the factor mu, and also from the error, residual error in J2 and J4. But having 3 measures, we can cut away the effect of the error over the first 2, over the quadruple and octuple of the gravitational field of the Earth, making a combination that contain in principle only the effect of gravitation of line steering, cancelling this J2 and J4 effect. This is the result we have for each 7-day point, an estimation, a calculated value for mu. General relativity said this is as time function. We see that we have a noise over that, but the points are distributed Gaussian around the expected value of general relativity, that is 1. To make a more precise analysis, there is common to build a commutative sum of mu that reduces the oscillation, and to fit this data and to make the measure of mu, we adopted a linear regression. In the past, a multi-parameter non-linear fit was used, and of course, if more parameter that you have, and it's more likely to introduce systematics. This is the final measurement of rest steering that is very close to the mu expected by a general relativity that is 1. This is the measure, and there are the statistics and the systematic error. In particular, the systematic error is 1.6%, and the main contribution are given by the residual gravitational field model and other periodic effect. Indeed, this measure is quite precise and accurate. Let's go to the second part. I will speak now about this second experiment, SaToR-G, that is a continuation of LARASE project, and in this case we want to go beyond general relativity, testing possible deviation for general relativity. Today I will speak about a constraint on long-range Yukawa-like interaction, but we can make a measure of PPN parameter and not linear in gravitational interaction and equivalence principle. Let's start with Yukawa-like interaction. What one can test if beyond the 1/r distance square of r distance dependence, if there are other terms that are generally expressed by alpha, that's give the amplitude, and lambda, that give the range of the interaction. Eventually, Yukawa-like term over radial acceleration would produce the secular effect over the argument of pericenter and mean anomaly. So we have to compare possible effect due to Yukawa-like interaction with the effect of general relativity over these two Keplerian parameters. The effect of general relativity over these two parameters are quite high, 3,000 millisecond arc year, and this is similar for mean anomaly. This is calculated for the three satellites we take in account usually. And this measure was just made a similar measure in 2014, and we want to improve the previous limit, trying to use the entire life of the LARASE 2, about 28 years, together with the LARASE. And as I said before, we prefer linear fit of the final measurement, the combination, not to introduce possible polarization. This is an example of what we can do, what we have done using the argument of pericenter of LARASE and LARASE 2. And in this case, we have then the precision of these two satellites, that of the pericenter of these two satellites that are combined in such a way to cancel the effect of J2. And the total precision is given by the gravitation general relativity expected effect plus gravitational perturbation on gravitational perturbation. In this case, we are working on this to reduce thermal thrust, as yesterday David Lucchesi explained. As you see, we have a lot. This is not a linear secular effect, but the latter oscillation due to the thermal thrust. A better combination can be built using pericenter, the argument of pericenter mean anomaly of LARASE 2, considering only one satellite, but with the two Keplerian parameter, we cancel all the same, the larger effect that is given by J2. In this case, we could make a better measurement respect to the past, to confirm we are in agreement with the general relativity with a systematic error that is lower than 1%. And this is the exclusion plot, and in this plot is reported that the strength versus the range. All the measure exclude this part of possible value. In 2014, the limit was here, and now the limit is lowered. Here is the level given by systematics. In conclusion, I presented these two experiments, LARASE and SaToR-G, founded by Italian National Institute for Nuclear Physics, that use laser tracking satellite for general relativity measurement. One of the main activity is to constrain, to model gravitational and non-gravitational perturbation. In the case of a measure that I showed today of lens steering precision, a very important improvement was done using not static model for our field, but time solution of Grace. And I can stop here. I think that everyone is thinking to the lunch now.
Thanks, Massimo. We have 30 seconds for questions. Anyone?
I have a question concerning the secular rate of the ascending node. How do you separate the impact of the lens furring effect from the de Sitter effect? Because the de Sitter effect also causes the secular rate of the nodes.
But it's modeled in our precise orbit determination. We use
slightly smaller
our
than
measurement is made modeling on general relativity rather than the effect we want to measure. This is the technique that was used several years.
Yeah, but the Sitter is only slightly smaller than the lens furring effect.
But it's modeled. That's in our analysis.
Okay, thank you.
And of course, there is, I would say better, that is taking account also in general relativity effect not that we measure over the systematics. That's, your question is right. There is part of the systematics that depends over how well we model the rest of general relativity, of course. Yeah.
But the Sitter is, let's say, roughly 60% of the lens furring effect. So if you neglect the Sitter effect, you're going
We
to...
don't neglect, we model it in our precise determination.
So you estimate lens furring, but you assume that the Sitter is right. So
with its systematic error, yeah. We can discuss about that.
Okay, thank you.
You're welcome.
It sounds like a good lunchtime topic. So, okay, well, thank you. That was a great kickoff to this session. We're going to continue after lunch. I don't know, Bea, did you have? Okay, go get fed.